So, as you remember, in the last video we talked about exponential functions, and weren't those just a great time? So let's kind of think about what we know, y equals 2 to the x. We know some stuff about y equals 2 to the x, right? We were able to plug in x values and get out y values, and we kind of dealt with this on what this is going to look like. If I put in 0, I get 1. If I put in 1, I get 2. If I put in 2, I get 4, 3, I get 8, right? If I put in a negative 1, remember we talked about how 2 to the negative 1, that would put it in the denominator. To the negative 2 would be 1/4, and then to the negative 3 would be 1/8. So I'm sure, as you were looking at the graph of that, I know you were thinking this, you were thinking, Sarah, as I look at the graph of y equals 2 to the x, and I think about all of the marvelous things that you've taught me about algebra, I remember us having a discussion about what it means for a function to be one-to-one, right? That is your natural inclination as you're just glancing at the graph of 2 to the x. I'm just going to graph a couple of these points. And random person I'm talking to out on the interwebs, you would be right. This function is one-to-one, right? Every input x has exactly one output y. That just makes it a function. But then also no two y values are shared, right? So if I take any two distinct x values, they have distinct y values. So you're absolutely right, random person. This is a one-to-one function, which in that case, right, means that it has an inverse. I know. I'm excited too. This is going to be pretty awesome. So remember what an inverse function does, right? So an inverse function, so let's consider y to the negative 1, which we are going to say is the inverse of 2 to the x. We don't know what that is yet, right? So what I do know about inverse functions is I do know that these inverse functions, say y to the negative 1, are going to take these x and y values for 2 to the x and they're going to switch them. That's what an inverse does. So now we have, 1 going to 0, we have 2 going to 1, we have 4 going to 2, we have 8 going to 3, then I have this 1/2 going to negative 1, I have 1/4 going to negative 2, and because this function, we know 2 to the x is 1-to-1, I know that this guy right here, whatever this is, I don't know what it is yet, I know that this guy right here is going to be a function. So this is kind of interesting, and if you kind of look at this and you kind of look at the mapping, like, okay, so 1 goes to 0, 2 goes to 1, 4 goes to 2, 8 goes to 3. So like what are we thinking about here? So it looks like what we have, like our input, right, is a number, and then our output are the exponents that I would have to raise 2 to. I should not use 2. I always use 2 and then I regret it because I say 2 so many times. But it's the order to which I shall raise 2 in order to get, right, this number that I'm plugging in. So look at my input. If my input is 8, what is my output? It's going to be the exponent to which I would raise 2 in order to get 8. If my input is 4, my output is going to be 2 because I raised 2 squared is 4. If my input was 16, what would my output be for this function? It'd be 4 because 2 to the 4th is 16. So that's what this function does, right? You plug in numbers and then it plugs out the exponents that you would raise the power of 2 to in order to get whatever that number is. So here's kind of the problem. So anyway, let's maybe kind of write that down. So this guy right here is the exponent to which 2 is raised in order to get, right, whatever my input is here, in order to get x, okay? So that's exactly what this function is going to do. It's going to be kind of an interesting function. We're going to have to figure out what it is, and here's the exciting news, you guys. This is a brand new function. I know, I'm excited too. It's so cool. And let me show you why it's a brand new function really quick. So if we took what we know from 5.1 and we said, fine, you know what? I'm going to find its inverse because Sarah taught me how to do this. And Sarah taught me that I switch x and y. And then I solve for y. Well, my friends, here's the issue, right? How do I get y by itself? I can't take like the root, that doesn't even make sense, of this function. Well, I guess it makes sense, but it's not going to work because I'm still not going to get y by itself. Somehow, right, we're going to have to get this exponent y, we're going to have to get it down off of the exponent. And that is where we're going to use what we call the logarithm. Dun, dun, dun. Man, if I was a good, if I was a better online lecture, I would have had some like music or something called there. So that's exactly what we're going to get. So here in this case right here, what we are going to define this to be, and this might be stuff that you've seen before, but I'm going to bring that y down, and what's going to happen, this 2, I'm going to move away. I'm going to move it across the equal sign, excuse me, and I'm actually defining a whole new function. And this function that we're defining is called the logarithm. So what I am going to define y to be, which is the inverse of 2 to the x, is it's going to be this brand new function called log base 2 of x. And that's what we mean by a logarithmic function. I'm sure you've heard of logarithms before. You've been at a party, people talk about them. You know, you've heard of them, you know, all the cool kids are working with them. But that's what a logarithm is, okay? It's just, we are going to bring that base over. The reason we say log base 2 also is because if you notice, this is the inverse function for an exponential function, right? And what does that 2 have to do with the exponential function? It is the base for my exponential function. So let us write that down as a definition. Oh my goodness, I was like told myself when I started recording this that I was not going to do that today, and I've done it twice. All right, so definition. This is an important definition. We're going to come to know and love logarithms. They are a super useful function. Calculus and beyond. Calculus and beyond. So this is called a logarithmic function. This isn't like a theorem or anything. This is a definition. The logarithmic function, and now I want to define this more generally, just like we defined, right, general exponentials as a to the x. I'm going to define this function to be y equals log base a of x. And a couple things here. X has to be greater than 0, and it actually can't equal 0, and we'll talk about why that's true here in a minute. So x has to be greater than 0, and a also has to be positive, and a cannot be 1, okay? So this logarithmic function with x greater than 0, a greater than 0, and a not equal to 1, here's what it does. It gives a number. It spits out that y value, right? A number y such that, so remember those y values, so let's go back and look at what we know here. Those y values, right, that it spits out, those are my exponents, okay? So it spits out a y value such that, and here's the thing here, a to the y equals whatever we're taking the logarithm of, okay? Another way to write that is that log base a of x equals y, if and only if, or this is true, if x equals a to the y. So another way to think of that is, if I have log base 2 of 8, what you're asking yourself is, to what shall I raise 2 in order to get 8? And what this function is going to spit out is that exponent, okay? Couple of notes here that are quite important. Log base a of 1. So think about this. This is saying, what do I raise any number to in order to get 1? Well, any number raised to the 0 power, right, is going to be 1. I hope that makes sense. And if you look here, right, you have 0, whoa, sorry, I'm just knocking out of the park today. 0, 1 now becomes 1, 0, right? So remember, this y inverse now is log base 2 of x. Yeah, sorry. So if I put in the 1 for x, I just thought I had messed that up for a minute, and I was like kind of freaking a little bit, but I'm all right. It's okay. So log base 2 of 1, then what do I raise 2 to in order to get 1? It would be 0. I hope I didn't confuse you there. Okay, so that's one interesting thing about logarithms, is that if I take log base anything, as long as that a is positive and not 1, if I take log base anything of 1, it's always going to be 0. Likewise, what if I take log base a of a, right? Look at what that's asking. To what shall I raise a in order to get a? Well, the way I can get a by raising it to anything is if I have just one of them. So again, look at what this is kind of I want you to see what this is kind of saying. If I rewrite this, this is 1 equals a to the 0 using kind of that form. Same thing here. This base right here comes across the equation and becomes a base for my exponent. This is a equals a to the 1, which makes sense. Okay, so that's kind of how you can check yourself before you wreck yourself. I can't help myself. I'm in my office by myself. I'm a little tired today. It's been a long day, and I'm recording a lecture for myself. Okay, so how do we kind of read this? So just some kind of notation a little bit, but so this guy right here, what this says, the way we read this actually is we say log base A of x, okay? And a couple things. Make sure that a is a subscript. I don't want to see any of this log of ax, right? That's not correct. I want to see log base a of x. Also, you could say the log, I'm just being a bit lazy, but it's read really the logarithm base a of x. I probably should say logarithm, but I'm not going to. Sorry about that. Anyway, that's what that is. That's our logarithm, and we'll talk about their graphs here in a little bit. But before we actually get to their graphs, what I would like to look at, and we'll do what I say, is I would like to look at a couple of examples. So I want to rewrite here what log base a of x. Whoa, I don't know why it's doing that. Let's get rid of that really quick and make sure we have this. So if I have, again, log base a of x equals y, that is the same thing as saying, right, x equals a to the y. So some simplification here. Let's look at just simplifying. So let's simplify the following logarithmic expressions and kind of get an idea of what this stuff means. So for example, something like log base 3 of 9. What you want to think of this as, this is asking what is 3 raised to in order to get 9? To what exponent is 3 raised to in order to get 9? Well, that's pretty obvious, right? Well, I would hope. It's pretty obvious that I would raise 3 to the second power to get 9. So, sorry, I'm getting rid of that. So log base 3 actually gives us a number. Log base 3 of 9 is equal to 2. Those log base 3 of 9 is the number 2. I know that looks a little bit weird, but that's what we mean by simplifying. Some other examples here, hopefully, that are pretty easy. Well, not easy. This isn't trivial. Log base 10 of 1,000. Again, what is this asking? To what do I raise 10? What exponent would I use on 10 in order to get, oh, I meant 1,000. There we go. In order to get 1,000. So what would I raise 10 to in order to get 1,000? That'd be 3. Okay, let's look at some other ones. What about log base 4 of 64? What do I raise 4 to in order to get 64? That is also 3. We can get a little more complicated here if we want to, so this would be fun. What about log base 6 of 1? Well, we know that one, right? We kind of talked about that one. What is log base anything of 1? Again, what do you want to think about here? Well, what would I have to raise 6 to in order to get 1? Well, that's kind of crazy, but what I'm going to raise that to is 0. So these are all, notice I'm putting an equal sign. I am so bold as to say that these are all equal together. Now, let's get a little bit harder. What about log base 5 of 1/5? Okay, so something like log base 5 of 1/5 is going to be it's not a problem. I was going to say it's going to be a problem. It's not a problem. What I just kind of want to think about is I want to think about, well, 5 squared is 25, 5 cubed is 125. I'm definitely not going to be getting, 1/5 by doing that. But what you have to remember is what other exponents can I raise 5 to? And that's negatives. So I can raise 5 to the negatives, or so I can even raise 5 to fractions, So what I want to think about here is, well, what do I know? A negative exponent, right, is going to take 1 over that. And notice here, if I rewrite it using this right here, is 1/5 equal to 5 to the negative 1? Yeah, sure enough it is. So we did that correctly. Okay. You can use fractions. Something like, what if I had log base 49 of 7? Look at what that's asking. What do I raise 49 to in order to get 7? It's not going to be a whole number. It's not going to be like 1, 2, or 3, right? It's not going to be a number bigger than 1 because I know that 49 is bigger than 7. It's not, I don't think it's going to be a negative because a negative would just put 1 over 49 or 1 over 49 squared or 1 over 49 cubed. But what if we raised 49 to the 1/2 power, right? Sure enough, I know that 49 to the 1/2 power is the same as the square root of 49, so we do indeed get 7 when we do that. Okay, hope this makes sense. Logarithms are important. If this stuff makes sense, you're going to have a pretty good time of, being able to kind of finish this. One quick one. What is, let's put G. What about log base 11 of 11? What do I raise 11 to get 11? That would just be 1, okay? We can also work, we can also work with just getting, this is just kind of a purely an exercise in getting used to writing logarithms, and eventually we're going to solve equations. Well, in the next section, we're going to solve equations that involve logarithms, so we just want to get used to converting between them. So let's take the, let's convert the following into equations involving logarithms, okay? And then we'll go the other way too. And then, we're going to look at the graphs maybe, and then we'll probably call it good. So these aren't going to be too bad. All right, so let's convert the following equations into equations involving logarithms. I'm not asking you to solve this. I'm just asking you to convert. So let's say I have 2 cubed equals 8. That is a true statement. Not much you can argue with that. And what I want to do is I want to convert this using logarithms. So again, what do I know? I know that log base A of x, if that equals y, right? That is exactly the same as x equals a to the y. So here's how I remember it, and you're welcome to remember it however you want as long as it's mathematically correct. If I want to go to a logarithm, what I'm always going to do is if I want to go from either, like this is an exponential equation and I want to go to logarithmic, or from logarithmic to exponential, I want to find the base and I want to move it across the equal sign. So in this case, what is the base? The base in this case is a 2, and I'm going to move it across the equal sign. When it gets moved across the equal sign, it changes to the other thing. So this is now going to become log, it becomes the base for my logarithm. So the base for my exponent becomes the base of my logarithm. And sure enough, this makes sense, right? Log base 2 of 8, look at what that's asking. What do I raise 2 to in order to get 8? And I would raise it to the 3rd power, okay? What if we had 10 to the negative 4 equals, what would that be? 0.0001? Yes, I think so. So 10 to the negative 4. Again, what am I going to do? I'm going to take the base. Well, where is a base? Well, I have an exponent, so that means 10 must be my base. I'm going to take it across the equal sign, and it changes to the base for my logarithm. So I'm going to have log base 10. We'll talk about log base 10. Log base 10 is kind of special. Oh, log base 10, you're so special. Again, so what if I had, 17 equals 5 to the x? Again, I'm asking you to solve this. I'm just asking you to rewrite this using an equation. So again, I'm going to find anything that's a base here. What do I have the base? I have the base for an exponent here. So I have 5. I'm going to move it across the equal sign. Now I'm going to the left. That's okay. Who cares? It's all right. Doesn't matter which way you write it. And so I'm going to move it across. Once it comes across the equal sign, it becomes the base for my logarithm now. No longer the base for an exponent, but now it's the base for my logarithm. This can also happen with e. So we're going to talk about 10 and e here in a little. Oh, that was crazy. In a little bit. They're actually kind of important. They're so important that we give them their own special logarithm. But I could have, I don't know, e to the t equals 4.6. So again, where is my base? The base is that cool number e that we talked about at the end of the last lecture. It's going to go across the equal sign, and it's going to become the base for my logarithm. So t equals, We're going to talk about log base E here in a minute. If you've heard about natural logarithms, excuse me, again, one of those things on the street that you hear about, that's what the natural logarithm is. All right, people, so now you're probably wondering, but Sarah, like, what if we go the other way? Can we go the other way? Oh, ask and you shall receive. We're going the other way. So example, let's convert the following equations now the other way. Convert the following to equations involving logarithms now. No, we just did that. 2 equations involving exponents. I'm glad I amused myself. That's important in life, you guys. It's important to really like what you do. Because even if you're sitting in your office all by yourself, you know, talking about logarithms, it makes you happy. Makes me happy. All right, so let's look at an example here. So how about log base 12 of 144? Right, isn't that 2? I think so. What do I raise 12 to get 140? What I raised 12 to get 144, it would be 2. Okay, so just like I said in that last one, I'm going to find the base and I'm going to move it across the equation and it's going to be the base for the other one. So I'm involving logarithms. I want to switch to exponents. So where's my base right here? This number 12 is my base, right? It's the base for my logarithm. It's going to come across the equals sign and it is going to become the base of what now? The inverse. So this is going to come across the equals sign and I get 144 equals 12 squared. I feel like, why am I thinking that's not right? It is right. It's fine. What about log base 10 of x equals 17? I don't know why I like 17. Again, I'm going to look for a base. What is the base that I have? The base right now is 10. We're going to talk about that again in a minute. It's going to come across the equal sign and become the base now for this exponent. You guys remember, these logarithms spit out exponents. So this 17 right here, if I rewrite it without a logarithm, that 17 best becoming an exponent if we do that correctly, right? So this will be 10 to the 17th, which I don't know what that is. It's a big number. I do know what that is. That's a 1 with 17 zeros. I do know that. What if I had, this is going to be a little silly, but what if I had p? That sounds like something I say to my 1-year-old son. I'm sorry, I did not mean to say it like that. What if I had p equals log base m of n? Same thing, you guys. Again, this p right here, when I'm done, better be an exponent. And this guy better be the base. I'm going to find my base. I'm going to take it across the equals sign, and it is going to become the base for my exponent. Okay, so what does this become? It becomes m to the p equals n. Okay, I hope those make sense. If you start working on these and these aren't making sense, you have to contact me or talk to someone who knows what they're doing about this, because as we move on with logarithms, as we go to properties of logarithms, as we talk about solving equations involving logarithms, all of those are going to be super, super important. Okay, so there are a couple logarithms that are special. I mean, isn't everyone special, which makes no one special, but let's talk about some special logarithms. And these are the logarithms that you will be able to do on your calculator. Now, some of you have these fancy calculators that will actually do logarithms with any base. And what they're doing is just a change of base. And we'll put down the change of base here in a little bit. But normally a regular old calculator, that everyone has, only does 2 type of logarithms. And those type of logarithms that we do, the first special type of logarithm is the log base 10. Logarithm base 10. And this is sometimes referred to as the common logarithm. Okay, so this comes up a lot anytime you're using like a metric system, anytime you're using really large, like 10 raised to really large numbers, or even 10 raised to really large negative numbers. Log base 10 is going to be super important because, again, the logarithm talks about exponents. So we actually say that log base 10 of x, let's say, that is going to be the same as just log of x. So if we don't have a base there, we automatically assume that it's base 10. I know what assuming does, but we're going to do it. Just like like a square root or a cubed root, that's a cubed root. This is a fourth root. The square root comes up so often that that's the one that we kind of think of as like maybe a common root. We don't put anything there because it comes up so much that we automatically assume if there's not a number there that it's going to be 2. Same thing here. If you don't have any base for the log, we automatically assume that it's log base 10, okay? And if you look in your calculator, you should have a little button on, let me know if you don't see it. You should have a little button that says, I think, I'm gonna actually get out my calculator here. Yeah, it just says log. It might say log X or it might just say log. And then in that little upper corner, you know how it has like the little blue numbers? It has like 10 to the x up here. So why does it have that? Because these two are inverse functions of each other. That's why it has it. Okay, the other special logarithm is our friend E. So logarithm base E. And this is what we call a natural logarithm because E is a freaky number, you guys. It comes up all the time. And population growth, population decline. It's our natural logarithm because it's naturally occurring in Earth. in nature. I'm a little exhausted today. My 1-year-old decided, you know, that he didn't want to sleep, and he doesn't need sleep. And would anyone like to play at 4:30 in the morning? And so we were up. So log base E of x. So again, if no number is there, we assume it's log base 10. If it's log base E, we have something called the natural logarithm. So we actually give it like its own notation. And we saw this is not a 1, this is an L, or a lot of times when you see me write it, I write it in cursive so that I know kind of what I'm dealing with and I don't have like a 1nx. But this is called the natural logarithm and it's ln. And if you look on your calculator, you'll see a lot of times it'll be capitalized, but you'll have a ln. And then, hey, what do you know? What is the, well, you've already seen e to the x because we did that already, but the e to the x, right, is going to be like that little friend that shares that key, and that's because it's the inverse function. So again, natural logarithm and log base E. A couple things about these. Sorry, I should have done it up here. But stuff that we know, right, of course, is that we already know is if I have, that is true for any base, but if I have log of 1, that must be 0, right? Because that's saying, what do I raise 10 to get 1? And then the other one that's just true for this one is if I have log of 10, that's going to equal 1, right? Because what do I raise 10 to get 10? That would be 1. Likewise for my natural logarithms, and these are the ones that are going to come up actually a little bit more often, but this is a very important thing to remember, that the natural log of 1 is 0. Again, what is that asking? What do I raise e to in order to get 1? I would raise it to the 0 power. The other important one of this is the natural log of e is just 1. What do I raise e to get 1? Or, excuse me, what do I raise e to get e? That would just be 1, right? What else? So those you can do in your calculator. So, you know, if I were to ask you, you know, what is the natural log of 4.5? You're just literally going to take your calculator, do the natural log of 4.5, and that's asking, what do I raise e to get 4.5? You would raise e to the 1.504077, blah, 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 right? Pretty easy to do. Put those in your calculator, and that's not too bad. Now, though, when we do things like, you know, if we're converting equations, which we saw before, so like if I had like e to the x equals 17, so instead of writing x equals log base e of 17, what I'm actually going to write instead is everywhere I see a log base e, I'm going to replace it with the natural log of 17. I hope that makes sense. Likewise, sorry, I'm going to continue on this vein for a moment. Wasn't really planning to, but you know, when you get the train going, it's hard to stop. What if I add like the natural log of x equals 4? So if I add like the natural log of x equals 4, one thing you might do is you might rewrite it actually with log base e of x equals 4, so that you, at least until you're really comfortable with these logarithms, because then you can say, okay, what is my base? It's e, so I'm going to bring that over, right, and this is going to be x equals e to the 4. Get used to that natural logarithm. We're going to use natural logarithm a lot. Okay, all right, a couple more things and then we're going to call it good. So the change of base formula. So you might be wondering, Sarah, but what if I really want to take, log base 4 of 17? I don't know why I'm on 17 today. What we have is we have something called the change of base formula. Now, for some of you, this might not matter because of the calculator you have, but what the change of base formula tells us is I can actually, and we'll prove this later on when we get to properties of logarithms, so you don't have to worry about that right now. But what this says is I can choose a log base, whatever I want, that's the a, and if I divide this part by m, log base a of m, and then I have log base a of b, that is equal to log base b of m. And again, I'm going to prove this for you. I kind of hate in your book that they give it to you without proving it to you. But one thing to remember about the change of base is that the base stays in the basement. Isn't that great? I stole that from my friend and colleague, Susan Hayborn. It's just amazing. So for example, like if I wanted to evaluate, let's say, what log base 3 of 12 is going to be. It's not 4, because what is this asking? What do I raise 3 to get 12? Well, in my calculator, right, I don't have a log base 3. But guess what I do have in my calculator? I have a natural log. So I could do on the change of base formula, my m in this case is 12. I'm going to do the natural log of 12 over the natural log of 3. Just try and stop me. I'm going to do it. The base stays in the basement. And if I put that in my calculator, natural log of 12, close parenthesis, divided by natural log of 3, close parenthesis, I see that this guy equals about 2.26. That's an approximation. Could I also have done, look, it doesn't matter what base you do, but be mindful, like you want to choose a base that your calculator is going to do, right? That's the whole reason we're doing a change of base. So you could have also done log of 12. Go ahead, I dare you, put it into your calculator. Log of 3, it doesn't matter what base, but I take log of 12. I don't know why I'm doing this on the video for you. Yeah, sure enough, we get the same thing. Isn't that cool? So I'll prove change of base for you when we get to properties of logarithms. Okay, people, we're at 32 minutes. Let's talk about graphs and then let's call her good. I'm gonna clear this guy out. Couple thing about the graphs of logarithms. Or logarithmic functions. Are they functions? They are. They are functions. Every input we get one and only one output. Remember, what are my outputs? They're exponents, okay? So let's really quick graph that 2 to the x again. Remember, 2 to the 0 was 1. 2 to the 1 was 2. 2 squared is 4, right? 2 cubed is up here at 8. And then I know 2 to the negative 1 is negative 1, or is 1/2. Oh my goodness, not negative 1/2. 1/4, 1/8. Okay, so I want you to see, here is the graph of 2 to the x. And what do I know about 2 to the x? Its domain is everything, right? Its range. Think about its range. So 2 to the x, here's what I know. Its domain, everything. Everyone's invited to the party. I can raise whatever I can raise 2 to whatever I want. However, its range, right? Because 2 is a no, you can't equal 0, Sarah. Because 2 is a positive number, I know that its range is just 0 to infinity, because I can never raise a positive number to an exponent and get a negative number back out. This is quite important, people. I can never raise a positive number to an exponent and get a negative number out. So what do I know about functions? Or excuse me, not functions. Oh man, I really wish I could draw better. What do I know? I need to practice. About inverse functions, you guys. What do you know about inverse functions? You know, my friends, that inverse functions are reflections about the y equal x line, and we're just going to switch my x and y. So this point right here, 0, 1, is going to go to 1, 0. This point right here, 1, 2, is going to go to 2, 1. This point 2, 4 is going to go to 4, 2. And this point 3, 8 is going to go to 8, 3, right? This is what an inverse function does, you guys. And guess what I know what the inverse of 2 to the x is? It's log base 2 of x. Here, this point negative 1, 1/2 is going to go to 1/2, negative 1. That point right there, negative 2, 1/4 is going to 1/4, negative 2. So you can see what's happening here. You can see my blue graph right here is going to be log base 2 of x. Isn't that neat? And that gray line, kind of a line, that gray bumpy thing is the line y equals x. So notice, what do we know about log? Can you guys see that? Let's go a little lighter so maybe you can see that. So log, ooh, that's a pretty color. Log base 2 of x, which is this guy right here, right? Log base 2 of x. What do you see? Hey, people, you know, right, that my inverse functions switch domains and ranges. Yes, you do know that. So the domain of a logarithmic function is 0 to infinity. Only positive numbers are invited to this party, people. And what is the range? Everything. Remember, we switch them. Again, think about what this function does. This is asking, what do I raise 2 to in order to get x? So the only numbers that 2 is going to spit out when I raise it to a bunch of different exponents are positive numbers. And then why is my range negative infinity to infinity? Because what is this guy spitting out, my peeps? Don't know why I just called you my peeps. That was weird. What is it spitting out? It's spitting out exponents, right? And what kind of exponents can I raise 2 to? 2 to. Anything. I can raise it to anything. Okay, so be careful with that with the graphs of these logarithmic functions. What can we do to the logarithm functions? Can I shift them to the right and to the left? Absolutely. You know, if I took log base 2 of x plus 1, that would be this blue line shifted to the left one. I could take log base 2 of x all plus 1. We went through this with the exponential functions. That would just be log base 2 of x shifted up 1. I want to show you a couple things really quick about the different bases of logarithms. Just like the different bases for my exponents made the graphs just look a little bit different. That's going to be kind of the same thing here. So if I have log, hold on one second. Okay, sorry if that looked weird. I just realized I didn't know how to do a subscript in Desmos. So I had to Google it really fast, and now I do know. So look at that. Okay, so log base 2 of x. So we put that in. You can see we have a nice function here, and we know that that is the inverse of 2 to the x. So if we wanted to do like y equals log, let's say, base 3, I feel so empowered now that I know that. Look at what we have here, right? So remember, we're plugging in what 3 is kind of being, not what it's being raised to, but numbers that would output, and then putting in its exponents, okay? So look at how these graphs are comparing. If I think of taking that green graph and reflecting about the y equals x line, that's going to be a function that kind of goes a little bit faster than that. And if you notice here, I want to show you, if we take the natural log of x, do you see that purple one? It lies in between the blue and the green, and that would make sense because e is about 2.71828. So e is close to 3, and it makes sense then that natural logarithm should lie pretty close to log base 3 of x, but not actually equal to it. Some other ones, you know, if we do log x equals log of x, that's going to know that that's log base 10. And of course, that guy is going to hug the y-axis a lot faster and then kind of grow a little bit more slowly than, you know, because it's going to take, you know, when would it spit out 2? It spit out 2 when I put in 100 because that's 10 squared is 100. So this guy right here, I'm not going to get y to be 2 until I'm out at 100. So that's why it doesn't quite grow as quickly. And again, if we reflected that, you're going to see that's an exponential function that grows really fast. All right, you guys, I'm almost to 40 minutes. I don't know why 40 minutes is like this magical thing for me. I think you have attention for 40 minutes, which probably isn't true, but hopefully you're pausing this and watching bits at a time. Other than that, there might be some applications with logarithms, and right now those applications are just going to be, here's a function that has a logarithm in it, and then evaluate some stuff with it. All right, I hope you enjoyed that. I did too. Next one, we're going to talk about properties of logarithms. Really good time.